Okay, there's one other question I forgot to do. I didn't realize I didn't do it. It's number 12. And yeah, there's number 13, and we'll maybe 14, we'll maybe discuss it. But we're going to use graphing technology for 13 and 14. Let's look at 12. Now, always understand what's being measured when they ask these questions. 12 asks, the position of an object is moving along a straight line in t seconds given by a distance based on time. That's what s usually is, distance, where s is measured in meters. Explain how you would determine the average rate of change over the first 6 seconds. Okay, let's just, before we do anything, and we'll use graphing technology, but let's understand this graph for a little bit of time and also understand where it's at 0 seconds and where it's at 6 seconds. Let's put a Cartesian graph and understand. Let's punch in 0 for t. So at 0t, we get 0 over 4. So we know that we have the point 0, 0. What about the vertical asymptote? Well, we look at the bottom here and we see when t plus 4 is equal to 0, t cannot be minus 4. So now notice that this is to the left of the 0, 0 mark, and since x measures time, see, this is always the x here, and this whole thing here is always the y. So in other words, I should encircle that t. Whoa, how come that didn't? Okay, it doesn't matter. Let's put it all back. Try to get rid of it. One more back. I should say actually x is over here on the right, and this is y. So since time is running along the x-axis, and this is way to the left, that's negative time. We're really not concerned about that, right? 0 to 0. Let's put in a 6 here. At 6, we get 18 up here, and down below we get 10. So we're talking about 1.8. So it's 6, comma, 1.8. And we'll put it about here. Now, what is 1.8? What is the y-axis? The y-axis is a measure of distance. So that means this object, at some point, probably on a curve, because we're talking about a reciprocal function, climbs through 0, 0 and reaches 6.8 and then continues to climb. The distance between the x-axis and this point on the graph, that's a distance from origins, from where it started. So let's just say it started at 0 distance here, and it slowly rises to 1.8 meters here. So it's sort of creeping up. The other thing we can do is we can find the horizontal asymptote. Now, these both have the same degree. So we look at 3 over 1, which means the horizontal asymptote is y is equal to 3. So you can see that 1.8, 6 comma 1.8 hasn't come close to the y is equal to 3 spot yet. Remember that this is x is equal to minus 4. So if I was to graph it or imagine it graphing, since I know things try to get close to the asymptote, it would be something like this in blue. And it would go through 0, 0, 6.8. And also keep in mind it would hug both asymptotes. So if I'm going to do it incorrectly, something like this, something like that. And we could just put the other mark over here for 6.8, right around there. So what does the average rate of change mean in this context? Well, it goes from 0 to 1.8 over 6 seconds. So you just take 1.8 and divide it by 6. And we can see that so here's how you take average rate of change, y2, which is 1.8, minus y1, which is 0, over x2, which is 6, minus 0. So that's why I just take 1.8 and divide it by 6. And we get 0.3. What's the top measurement? What's y? Meters. What's the bottom? Per 1 second, or just per second. That's always what meters per second means. It means per every single second. And that's actually what all units are. The denominators are always 1. So that means this object on average is moving 0.3 meters away from origin, wherever origin is, per second. That's the average rate of change for B. It also answers this. Explain how you determine the average rate of change. So I take y2 minus y1 over x2 minus y1. What does average rate of change mean in this context? Well, it says this object is moving in a straight line. I know we see a curve, so it's hard to imagine a straight line. But it just means the object is going in one direction. And I want you to notice something. In the first second here, it's clear the object has gone quite a distance. Whereas in the next second, it's clear the object has not gone a big distance. So this object is slowing down. So even though it's in a straight line, when it first starts, whichever direction it's going, it starts fast, then slower, then slower, and then slower, and slower, and slower. And it's very tempting to say this object's moving in a curved line, but this curved line simply measures distance based on time, not direction. That's a vector. Just the distance over time. Once they told us it was going in a straight line, it simply means this object is moving fast at first, then slower, then slower, and slower. That's what the curve means. Compare two ways you would determine the instantaneous rate of change at 6. Okay, well, you could use 6 as a middle point, and you could do 0.1 to 0.001 to the left and 0.001 to the right. So you could take an average rate of change, or essentially an average rate of change between 5.99 and 6.001. That would use the 6 as a middle. Or you could skip that entirely, and you could use the other equation we learned, which is we can just take the original point and add h, and subtract the f of 6, all divided by whatever our h is. So that would mean if I do here, and that's the more likely one I'm going to use, and the smaller h I use, the more accurate I get. Now we know f of 6 is 1.8. So that means f of 6.0001 should be roughly 1.8. Let's see what it is. 3 zeros, 3 zeros. Always make sure your h matches. So we're going to take f of 6.1, which is 3 times 6.0001, and I'm going to put that in memory, equals, and I'm going to divide it by my memory. I'm going to open brackets, my memory, plus 4, close brackets. It equals. And sure enough, we get something that's very close to 1.8. Now we're going to subtract the 1.8. And now I'm going to divide it by my h, 0.0001. And I get this as my instantaneous rate of change. And of course, the units are still meters per second. That means at that very moment, that object is moving much slower than the average rate of change, which was 0.3 meters per second. It's moving 0.119 meters per second. Or if you want to convert it, you can do this. It's moving roughly 120 centimeters per second. And you can even convert that original 0.3. 0.3 meters per second is the same as 300 centimeters per second. So you can do all sorts of conversions of your units so long as you keep it consistent. So it's quite clear that the instantaneous rate of change at 6 seconds is about a third the speed as it was the average rate of change. Compare the two ways. Which way is easier? I find this last method the easiest. What does the instantaneous rate of change mean in this context? It means it's slowing down. It means it's clearly this object is slowing down. Let's see if I can do 13. There's no promise I can, because 13 is going on a strange esoteric thing. And as I said, for 13, we're going to use a graphing technology. And this is a specific, I won't say puzzle, but well-known graph. And we're going to do it as f of x is equal to 4x divided by x squared plus 1. You're going to see that this x squared plus 1 does not have a vertical asymptote, because there's no way that can equal 0. Sure enough, we get a shape like that. Determine the equations for the tangents at the points where x is equal to minus square root of 3, 0, and 3. And interestingly enough, I bet you, let's use a is equal to square root of 3. Let's make it negative. And let's find the instantaneous rate of change at a. Let's make our h very small. We have to make h extra small because our a is quite small. So we do f of a plus h minus f of a, all divided by h. And we get a rate of change that's essentially indicating 0.5. 0.5. So that means the rate of change at negative square root, rate of change at negative square root 3 is equal to 0 0.5, whatever units, unit per unit. Okay, let's find out what it is at 0, and I'm willing to bet it's going to be the same rate of change. We're going to make our A. Let's make it plus 3. And this time, let's go back to what it was. It was, oh, it's negative. Let's not forget that. It's negative. So that means right about here, negative square root of 3 is bigger than 1. It's right about here. It's going down. Let's mark it on our Desmos to see where that is. Negative square root of A. Well, let's just do A, comma, f of A. And we'll label it. So this is that spot. Now let's make our A positive just to see how much that's the same. And there we go. It's that same spot, but on the opposite side, right? That was over there. This is the 2 positive version. And it also has a negative slope. And that's because these 2 spots are essentially mirrors of the same graph, because this thing mirrors through the origin. And so it's obviously going to have the same slope at those same spots. And then finally, we're going to, so the positive square root of 3 has the same slope as and now we're finally going to do it when A is 0. And we discover a slope of 4. So it's climbing quickly there, which is also equal to the square root of 3. But the instantaneous rate of change, IROC, at 0 is positive 4. How would we determine a line of tangent, which is what I believe they've gone for each time? Okay, well, let's go back to our square root of 3. And we can do this for both positive and negative. We've determined that our rate of change is negative 0.5, so y is equal to negative 0.5x plus b. We just need to figure out our b. Well, fortunately, we have a y and an x. Y, and so that means if I rearrange this, b is equal to y plus negative 0.5 of x. So plus 0.5 of x. That's what b is equal to. I can just get rid of b, and I can plug in my values of x. And the nice thing is I can just put in a and f of a here, and I get my lovely b. So now I have all of my components. That's my b. So I just go back and put in my a, and I put in now my b. And there we go. We have a tangent line. And you might say, hey, it cuts through to the other side. And yeah, that's because this thing curves back down. But that's the tangent line for that point. And it should indeed go through. Didn't quite get the right point, though. So that makes me think I didn't quite get the right graph. So I'm going to put it all as what the lines are. Y is equal to negative 0.5 x. And then what's b? Plus b, as I said, is going to be f of a plus or minus a. Where's that green line? Did I get it right? Oh, okay, it's on the wrong side. Let's try plus a. That's also right. It could be, since b, mx, oh, you got to have the mx in there, plus m. Almost. There you go. So that is far more accurate. So now I just should figure what this is and just plug it in. What's this? Ah, it's because I rounded up too much. There we go. Now guess what? This is going to be the same slope as up there. I would just have to change some of the lines or some of the numbers. So I'm going to copy that whole thing. I'm going to keep the slope, but this time I'm going to make it plus. And voila, I've got the slope tangent of the other one. Now the slope of this one is going to be slightly different. Or that's the line of tangent of this one, because this time we have a 4x plus b. We just don't know b. Well, we know that at 0, it's 0, 0. So if I put 0 in here and 0 in here, b is 0. So that means the line of tangent is just going to be that. And we might as well make it a different color from our graph. get to it by this way. There we go. And we'll make it orange. And we'll make it purple. And there we go. We have all three lines of tangent. Notice it forms sort of a parallel lines up here. And that means you could even find where they cross through purple and black. Let's see what else they ask in this question. Don't know why they made us do this. Pretty straightforward. Determine the equations for the tangents. Yeah. Determine the instant rate of change at point around 0.00. Then determine the instant rate of change of this instantaneous rate of change. Wow. So they want us to take the instantaneous rate. Interesting. I don't know if I'll bother with the second part, but we'll focus on 0, 0. We'll just make our A0. So they want to know what? They want us to know, determine the instant rate of change. Certain numbers around the point. We just did that. It was 4. It was 4 right there. And then they want us to know the instantaneous rate of change of that. Well, that's always going to be a straight line. So since this is the tangent, the instantaneous rate of change of a line is going to be 4. So the answer would be y is equal to 4. And the instantaneous rate of change of a flat line is 0 because it doesn't go up or down, a horizontal line anyway. So I'm not quite sure what they're getting at. So the instantaneous rate of change of 0, 0 is 4x, or it's actually 4. And when you take an instantaneous rate of change of a number, it's 0. It's a flat, it's a horizontal line. I think that's what they're getting at. Stupid question, really.